And welcome to our final discussion on Chapter 9, and then we'll jump into a little bit of Chapter 10 tonight as well. But we are going to start with Chapter 9. And last week we left off talking about the different logic families, right? We talked about the CMOS, we talked about the TTL, we talked about the ECL, and what those differences were. And, we had the totem pole output stage, and we had the open collector, and, we talked about how things sync or source from the gates, either back in through the bottom transistor, or they source from the top transistor out the output. So we got into all of those discussions, and now we're going to look at, okay, what happens if you wanted to go from a TTL to a CMOS, or what happens if you want to go from a CMOS to a TTL, because it's not as simple as, just putting the output into the input of the other one, all right? And the reason why is because what you see right here. And you see that for a TTL chip, the output high, typically anywhere from 2.4 to 5 volts, okay? So look what happens down below. If you have an input high, the minimum is 3.33. So what happens? What if you have a 2.5 volt high output from a TTL? Well, it's going to get recognized as uncertain in the middle there because it doesn't meet that 3.33 volt threshold. Okay? Oh, somebody said you didn't see this. Boop, here we go. Sorry about that. So, just to reiterate what you couldn't see, so there are, two different, essentially, regions here, right, for each type, for the TTL and for the CMOS. So this is what I was referencing. You can see that up here for a TTL, if we were going from TTL to CMOS, okay, the output high, the minimum is 2.4. So my test case was, okay, let's say I have a high out of a TTL at 2.5 volts. Look at what the input high minimum is on a CMOS. It's 3.33. So that means that if I have a 2.5 volt out here, it's not going to recognize it, or it may or may not. It's in the uncertain region, right? That's kind of that floating region. If it doesn't meet that 3.33 volt threshold, it's not going to accept it as a 1 or a high. So you've got an error there. So this is why you can't just hook up any family to any family. You have to interface them somehow so that when you do have an output high that's only 2.5 volts, say out of a TTL, that it gets raised high enough to where it's considered a high on a CMOS. Okay? So as you can see here, it says an output of 2.4 volt falls into the uncertain region of the CMOS. Okay, so that's a problem. So here's what we do to solve it. Much like the open collector, right? We talked about how do you make sure that you have a high? Well, you have to have what we call a pull-up resistor. And they're typically always 10K and they're connected to 5 volts. Okay? The pull-down resistor is always about 100 ohms, and that's always connected to ground. So if you wanted to pull something low, you put it in series with a 100 ohm resistor and make it go to ground. And if you want to pull a value up, we typically connect it to 5 volts and then put it in series with a 10K ohm resistor. Okay, so we take the output of the TTL chip, right, which could be 2.4 volts, and so what it does is it raises it, right, because if it's a high, then we know that the TTL is sourcing out a current this way, right, which means that there is no ground for this to sink back into, and so what it does is it makes that high actually 5 volts. Okay, it'll actually pull it up to this top voltage. Okay, so if you have this connected here, 5 is the highest, and so that's what you would read. So that would actually pull that 2.4 up to this value right here, 5 volts. Okay, so but that's only the case where you see here, if you had a low voltage high, like you see 3.33 right here, it's not even anywhere close to that. It's a whole volt away, or 900 millivolts away, whereas the input threshold is 3.33. Okay, now if you have a low output, I think you're okay, right? Because the input high low is 1.67 volts, and the maximum you're going to get out for an output low is 0.4 volts. So even if it was at the highest it could possibly be for a low, which is 0.4, that still falls within this input high low region, so you're okay there. The problem comes in when you're trying to output a high from TTL and getting it to read as a high in a CMOS. Okay, so that's why we use that pull-up resistor. Now, if you go the other way, right, obviously you don't want to pull it up because you know, a CMOS, you know, or a TTL chip is going to be a little bit lower voltage threshold, so you can't just use a pull up or a pull down resistor. It says right here, the CMOS cannot sync the input low required by the TTL gate. Okay, so remember, if it's a low on the output, that means it's going to sync back through that bottom transistor. Okay, and so the output low here, right, it says for it to be an output low, it has to be at least the maximum is 0.51 milliamps. Okay, and so this is actually going to output 1.6 milliamps. You know, there's not enough room there. It's not going to work, right? It's gonna get held up. It's only going to allow 0.51 of it to go through. And so essentially it acts like a block, okay, and it remains high. So to satisfy this, we actually have to put another IC gate in between there, and it's called a buffer. Okay, so I guarantee you these two types of questions will be on the exam. What do you do in this situation? You have to use the pull-up resistor if you go from one to the other, and if you're going the opposite direction, okay, you have to put a CMOS buffer in there. All right, so you know, you can see here basically it changes the signal to condition it to where it will act appropriately as a TTL signal. For, you know, these are 7400 series are always TTLs, the 4000 series are CMOS. Now you'll remember from our discussion last time, and I'm not going to pull it up because I don't think it's close by here, but we talked about how there are, okay, here it is right here. So the 74C and the 74HC series, these are direct pin replacements for the TTL chips. Okay, so they are pin compatible, and I believe they have the same operating characteristics that allow it to play nicely with other TTL chips. Okay, but if it's 4000 series, that's the original CMOS line, and if you want to go between the 4000s and the 7400 series of the TTL, then that's what you have to do. Okay. All right, and so you know, this is talking about the worst case. So that's kind of what we just did. Is we went through a few worst case scenarios for interfacing. So just remember those two things. What happens when you go from TTL to CMOS, and what do you do when you go from CMOS to TTL? Okay. Sometimes you need to dramatically change what the voltage is on something to make sure that it doesn't fry another piece of, you know, a different gate or whatever, or another IC chip, or maybe this is going into some op amp or something. And so if you need to shift the voltage level, you know, it's not as simple as just a pull-up resistor where it's going to pull it to 5 volts. You know, you can shift it to pretty much any voltage that you want, and you know, you would have to use an IC to do that if you wanted to raise it. Okay. Now what about okay, so that's using a level shifter again, but what about ECL? Okay, remember we talked about how quick they are, but how much of a power monster they are as well, right? They're not very efficient, but you know, they have speeds that are pretty much top of the line compared to the CMOS or the TTL. Even the fast CMOS chips aren't as fast. So anyway, I'm not going to ask you about interfacing between these because we really don't use ECL that much anyway. You know, all of your gadgets and devices, they don't want a big power-consuming IC chip in there. They want everything to be, you know, to consume less and less and less power and take up less of a footprint. And so, we really don't use ECL that much, so I'm not going to require that you know this for the exams or the quizzes, okay? So let's talk about what some of you have already gotten in the mail, by the way. Some of you obviously already had the DE10 previously. Some of you ordered it, and I don't know if this is the case for everyone, but a few people that ordered it last week still have a ship date today, as of today, that still says September 8th, and they've gone ahead and shipped them out this previous weekend and didn't change any of the statuses. And so, they started showing up at people's doors even though their account said that it was still pending, or still had a future ship date of September 8th. So that is what we call an FPGA, right? A Field Programmable Gate Array. And basically what it is it's a whole lot of different gates, from that we talked about in 112, right? And it makes all of these internal connections, okay? And so there's thousands of different gates that you can choose from. It makes all the connections internally for you every time you download a program. And so, it does have inputs and outputs that you can use as well, like exterior. Like if you wanted to talk to an Arduino or something, there's a mechanism for that to happen. So it says each manufacturer of PLDs has different electrical characteristics, and it says set the VCC input output to the required voltage for the input output ports. Okay, so you can actually determine what type of chip you're using, and then change what these voltage levels are. Okay, so just to summarize all of Chapter 9. So it says there are 3 stages of internal circuitry of a TTL IC. We didn't really cover that because I don't want you to get down into those woods. Input, control, output. I just want you to get under your belt the notion of syncing the current through that bottom transistor versus sourcing it out in the top transistor. Okay. We talked about the actual, what the average high and low levels are for output voltages for the TTL family. We talked about what propagation delay is, and that it's down in the nanoseconds typically, and something that can do, when we're talking about propagation delay, it's if you have a stimulus on the input that causes the output to change, how long does it take from that input change to the output change? And you try to get that as low as possible, because that means that your system is going to work that much quicker. So if you can get them, it's typical for them to take about 15 to 20 nanoseconds, like on the 7400 series of the TTL chips. But you can buy them in different types that allow you to go much quicker. Like there's a few that'll do 3 nanoseconds, right? Especially the CMOS chips. Talked about the rise and fall times, 90% and 10%. Open collector outputs, and they have to have, it says open collector outputs are required whenever logic outputs are connected to a common point. And we talked about this too, the different families that exist. We talked about the CMOS family and the differences between the two. Emitter couple logic provides the highest speed, but very, very high power consumption, and it's not very popular. And they talk about the speed power product, where you talk about how quickly it can process a high to a low or a low to a high, and the power consumption. How much power does it take to do that? And so you want this to be very low, and you want this to be very low. And so if you have a very low speed power product, the better, as you can see here, just generally. And then if you have to interface between the logic families, you have to think about, first of all, are you going TTL to CMOS or CMOS to TTL? And then what do you need to do in each one of those situations? Okay. All right, so let's mosey right on into Chapter 10. And so you'll remember, some of you will remember, if you took the class recently, that I told you, if you had me, that we would go through the first 5 sections of Chapter 10, right? And that in this class we would cover the last half. And so what I'm going to do right now is essentially go over the part all the way up to the JK flip-flop. I'm going to talk about the SR. I'm going to talk about the different orientations that we can write it in using basic gates. And then I'm also going to talk about the D flip-flop, where we don't have that one unused condition, if you remember what that even means. Okay? So, yeah. So prior to us talking about flip-flops, we didn't have any way to store any ones or zeros if we wanted to do that, or to recall whether something was high or low. Okay, so up till now we have just used what we call combinational logic, where you can have a lot of different gates feeding into other gates, and then ultimately you have, you know, 1 or 2 or 3 separate outputs. Okay, or you just have a single output, right? You could have 10 gates that funnel down to a single output. So what happens is if you have all these inputs that are turned on at the same time, you know, minus a little bit of propagation delay, that output or outputs are going to have an immediate, essentially an immediate reaction to that stimulus, okay? And so, you know, it's constantly changing, but you're never retaining the state of anything. You know, maybe you want to know how many times something, you know, went high in a certain period of time, and you don't have any way to count that. Right? So now, with this orientation, where we have this feedback mechanism, what they call the cross-coupled scheme, excuse me, is that the output of one gate, in this case we're using NORs, that the output of one gate feeds back in as the input of another, and this output feeds back in as the input of the other. Okay? And if you remember, the SR stands for set reset. And so what this is an asynchronous set and reset. Asynchronous just means there's no control mechanism. There's no control line. There's no timer or clock pulse or anything like that. It's just whenever set and reset changes, there's an immediate change on these outputs, minus the propagation delay. Okay? So if you remember from this, if we have a 0, 0, that is what we call the hold condition. And it will actually have whatever Q and Q naught were before, that's what it will retain. So if you see a 0, 1, which is what the example is here, you have what we call a reset condition, and where, I'm sorry, this is the set condition because set is up here. So set is 1, reset is 0. That is the set condition. That means that Q is high and that Q naught is low. Okay, if you have the opposite of that, if you have a 0, 1, this is what we call the reset condition. And so Q becomes 0 and Q naught becomes 1. Okay, now like I said, let's say that we just got this set put on Q and Q naught, and then we go to a 0, 0, which is a hold. Since Q and Q naught were both 1 and 0 respectively, that's what they remain. That's what the hold condition means. Whatever Q and Q naught were, that's what they will remain to be in the hold condition. Now, in the situation here with the SR of 1, 1, that's what we call the unused condition, because that actually pulls both of these high, and that's no good. You don't want to. There's no use in having that condition, because these are supposed to be opposites of each other, Q and Q naught, right? So if one is 0, the other is 1. That's just the way it is, right? So we can express this in what we call a truth table, and we look at all the different possible combinations, just like we did with the logic gates themselves, if you're just talking about an AND gate or whatever. Now, this is the inputs to the SR Flip Flop system, right? Because it's actually 2 gates that we're using in this scenario right here. So you can see here, you know, if we have 0, 0 on the input, that's the hold condition, no change. Whatever Q was, Q remains. Whatever Q naught was, Q naught remains. And I'm sorry, that it actually pulls them down low. The high pulls them both low, which is no good. And so here you have the set condition where you have 1, 0, and you have it doesn't matter what Q was before, it automatically goes to 1, and Q naught goes to 0. And if you have the reset condition where you have 0, 1, the flip-flop resets, you whatever Q was before doesn't matter, because now it's 0 and Q naught is 1. Right? And again, we don't use this condition in the SR flip-flop because it pulls them both low, and that, you know, that violates Q and Q naught, because they shouldn't ever be the same. Okay? Now, there is a different configuration that you learned called the cross-coupled NAND scheme. And one of the things that I always point out is I used to have you actually draw these out when you do the exam. And I think I still may do it this time. You just have to take a picture of it. But one of the things I had said is make sure you have this written down in your notes and make sure that you have this one written down in your notes. So you can see here in the cross-coupled NOR, there is no inverters. There's only 2 NOR gates. That's it. And so if you have set on top and you have reset on bottom, these are going to be flipped, right? Q is down here on the reset, and Q0 is up here off the set NOR. But when you come down to the cross-coupled NAND, it's flipped, right? Here's the set on top and the reset on the bottom, but now Q is up here out of this set NAND gate, and then Q0 is down here with the reset NAND gate. Right? So the only difference is you're swapping out the NAND gate, or I'm sorry, the NOR gates for the NANDs, and then you're putting an inverter or a NOT gate in front of this input. Okay? So this configuration and this configuration will both give you this same function table, or truth table, if you will. Okay? And that's what he's showing you here, that they're the same. All right, now we do have a different way that we can write this if we just wanted to use the block symbol for it, where, you know, we have essentially a rectangle, and it's one of those things where you say, well, why? I know what's going on inside the box, and so this helps me visualize actually designing and using the SR flip-flop for different things. So, you know, some of them, I guess it depends on what you're using, but this one has a dedicated Q and a dedicated Q0. Right? This one just uses the same Q, but then this one shows an inversion on the output here. Right? Remember, we can show inversion with a triangle, with a bubble. We can also show it in the Boolean, you know, using the actual symbols, the alpha symbols, you know, with a bar over the top. Sometimes you'll see a prime next to it, you know, like a prime. But typically, you know, when you see the stuff in the Clyde's book, it's always with the bar over the top. So this is what it looks like if we were to use different SR values as inputs here, and you can see how Q, which is the output of the flip-flop, you can see how my kids are just ran through the house. Who knows what's going on out there? My door's locked though. So here's the S and here's the R, and you can see here we have an initial set condition because I have a 1 and a 0, so Q is high. Then we go into a 0, 0, which we know is a hold, right? And so whatever Q was before, Q remains. Then we go into a reset condition because we have a 0, 1, you can see here. And so now we transition from a high to a low. The next little segment of space here is, or I should say segment of time, is a low, low, which is a hold. And so since Q was already low, it remains low. Okay, then we come into a 0, 1 condition here at this point in time, and that's a set, and so Q goes high. Then we go back to a hold. Since Q was high here, it remains. Okay, and then again we go into a big reset here, and I say it's big because the pulse is high, but you know, regardless of that, even if this went back into a hold, this one is going to still stay low. So that pulls it from high to low into this reset. And then it does go back 0, 0 here for another hold, and since Q was already low, it remains. And then we go back into the set 0, 1, and it pulls it back high, and then it holds it for this last little bit of time. Okay, so when you go back in and read through chapter 10, this is what Kleitz does in all of his timing diagrams. I think it's pretty, I like what he does because he's showing you at every step of the way what condition. You know, when I say condition, I'm always talking about whether it's in the hold or the set or the reset, okay? He analyzes what happens at every point and what condition you're in based on the input. So this is the full, I mean, this is the full explanation of what happens when you have different inputs on an SR flip-flop, okay? So this is a good one to come back and reference. So here's an application where this might be used, because that might be your question, like why would you need just a single bit? Well, a lot of times these single bits are connected to a switch, right? If you're familiar with any manufacturing process, they have all kinds of limit switches, temperature limit switches, pressure limit switches, and all kinds of things that are in their safety mechanisms. Because if you say that this thing can't get above 170 degrees, or I want to shut off some pump, okay, and it gets above 170 degrees, and you have a limit switch that clips at 170, it'll automatically open itself up and turn off that motor, okay? So we can then take that information, the fact that it was tripped, and then put that through some digital circuitry and record. Like in this one, it's recording the time of day. Now, whenever I discuss this, I still have yet to figure out how, we've got 4 bits here, and so we can go from 0000 to 1111, which is 0 through 15, right? If you remember that from 112. So even if you use all 16 possibilities, that's only 16 out of 24 hours in the day, and I don't know a good way to break that down unless you're just going to do 12 hours and 12 hours or something. But somehow he has decided that 0 to 15 is going to represent the time of day. However that's done, okay? So that time of day is going to keep processing and keep moving throughout the day, however these bits come to these inputs here. And so these act kind of like strobe gates, right? Until, because they're all AND gates that feed into the set here, and notice how the reset of each one of these is tied to ground unless you hit the reset switch and it'll clear them all. But in the normal position, it is in this selected switch to ground, and so all of the resets are already pulled low. So it's either in a 00 or it will set if this temperature switch goes high, right? So this is going to click on, and those inputs are going to change, but nothing is going to happen to the set condition until this thing goes high, because there's going to be a 0 on each one of these inputs, and so it doesn't matter what this is doing. It matters, because this is going to be tied low all the time until you have an issue. So the idea here is at the time of day, when this temperature switch flips and goes to 5 volts, that puts a high on each one of these inputs, and essentially that's going to allow 2 sub 2 to the 0 through 2 to the 3rd to pass through those AND gates. Some of the results will be 1, some of them will be 0, but it will essentially pass those values through to these set of flip-flops, right? That is then going to change the Q output, and it's going to retain what that last sort of timestamp was, okay? Because you're setting the flip-flop, so you're changing the output and forcing it high and leaving it high. That information then can be sent to a microprocessor, and you could have it trigger an alarm, or you could have it trigger a pump to shut off, or you could have it trigger just about anything, a loud siren, or a big red light that flashes or something. I don't know. But you have information now that allows you to record what time of day that happened, and it keeps it there. And then you can also use that information in, like send this to an Arduino or something, and then have it do some other function, right? So that's the idea here in this example, just to kind of show you how this kind of stuff can be used at a very fundamental level. Now, we also talked about the gated SR flip-flop. Now we're starting to do a little bit of synchronous work, okay? Because, set and reset are the asynchronous inputs, right? And so, if you have a 0, 1, that's a set. If you have a 0, 1, that's a reset, okay? Now, here's the caveat with the gate enabled, is that if this is not high, it doesn't matter what set and reset are, it's not going to put them through. This is always in a hold condition, because this is, you can see here with the pink, this is the actual flip-flop itself. This gated circuitry in front of here is essentially like an enable. Well, it is called an enable, right? So if it's high, it's going to pass through set and reset. If it's low, whenever you have one of the inputs of an AND gate tied low, the output's always going to be low, right? That's a Boolean rule. And so, it's always going to be in a hold condition, because set and reset, these, what they're calling here S sub X and R sub X, the output of these two gates here are always going to be low unless this is high. Then it will pass them through. Okay? So asynchronous, output responds immediately to the input. Synchronous, output responds in step with a control input. And it could be as basic as a simple input like this that somebody uses a push button to, to push it on and off. That's still a synchronous system. Whereas if set and reset, as you saw in the previous example here, there is no control input. Whenever set and reset change, you get a change on the output Q here. Okay, so if you have a gate out in front, essentially you're enabling those inputs or you're disabling those inputs. And so the truth table looks a little bit more complicated because we have more possibilities, right? If you have essentially 3 inputs, then you have to go all the way from 0, 0, 0 to 1, 1, 1. Whereas, if we're just talking about the SR condition here, right, we only have 4 because there's only 2 inputs. So it's always 2 to the n in terms of how many combinations that you potentially have, right? So the gated SR has 8 because that's 2 to the 3. So, now 4 of them are when the gate is low, and so it's kind of irrelevant what happens with SNR. The easiest thing to do here would just to be, this is a picture, but if you just had one line that said gate 0, you could put an X here and an X here because it doesn't matter what set and reset are. It's just going to be Q and Q naught because you're in a hold condition. But they went ahead and showed you all 4 possibilities when the gate is low. Okay. Now, just because we have a gate in front doesn't mean that we are now going to use the 1, 1 condition either. So it still stands that the other 4 conditions here, where set and reset actually matter what they are. It looks exactly the same as a regular SR flip-flop. The only difference is now we have these 4 gate conditions, 4 gate condition possibilities where the gate is low. And here we go. If you have this other kind of condition here where you only have a single data input, we call this a D flip-flop, a data flip-flop. So you can see here with the previous example, we have a set and we have a reset. There's 2. Here, this cures us of the situation where we have an unused condition. Because if you only have a single data input, the only possibilities are 0, 1 or 1, 0, right? Because here we have, if D is high, D is going to get inverted here and become a low before it goes down to the reset. But now we only have one data line that we have to worry about controlling this flip-flop. Okay, it's still gated, but now what we say is that Q either follows D, right? So if data is high, that's a set condition. If data is low, that's a reset. Those are the only 2 conditions. There is no hold condition here, okay? And the only hold condition here is when gate is low, right? Only this time we don't call it a hold condition, we call it being latched. So we kind of latch it shut. Either we latch it high or we latch it low. But while the gate is high, you can see here we say that Q follows D. That's a very common term. Q follows D. So while the gate is high, Q follows D. They have an identical waveform. And then once the gate goes low, we latch in whatever Q was. And Q was high, and so we latch it in. It works just like a hold. Now you can see that even though D changes in this period of time right here, Q just stays latched. It's waiting for this gate to go back high, and then Q follows D. So basically the entire time the gate is high, it's going to pass D right through to Q. Okay? And then you can see here, we go from high to low on the gate when we go into a latched condition, and so since Q was already low, it stays low, even though this changes high and then low and then high again. Then we come to where the gate goes high again, and now Q follows D. So D is high at that point in time, and so we pull this up to a high, and then it follows it out, and then we latch that low. So it's kind of, the latch you can kind of think like the hold condition. Okay, but with a D flip-flop, like I said, there is no third hold. It's just if you have a gated D flip-flop, your hold comes in when you latch through the gate. Okay. What else do I want to talk about through here? All of these are about the VHDL. let's see here. Okay. So this is a 7474 IC, and you might use this in one of the labs that we do. So I just wanted to reiterate what you might see here, because we did talk about this one in the 112 lecture. So you only have the one data input here, okay, and so that's going to change Q, and then you have Q naught, obviously. But there's a couple of other inputs that we have to look at, right? So the ones on the top and the bottom are the asynchronous set and the asynchronous reset. At any time, regardless of where the clock is, if you have an asynchronous low, which this is an active low, because you see that, if you remember that term, active low means that if you want it to remain unchanged, you leave it as a high. But active low means that when you go from a high to a low, it'll activate that input. So regardless of where the clock pulse is, if you have an if you have an asynchronous reset, it'll change Q to 0 and Q naught to 1. If you have an asynchronous reset that hits, regardless of where the clock pulse is, it's going to make the output high, and then Q naught is going to be low. Okay? Now, the clock pulse is kind of like the gate, all right? But in this case, we're using what we called edge triggering, all right? Now, you remember from what we just looked at, this does not have edge triggering, okay? While the gate is high, it's just wide open, right? Q follows D because it works like a latch, right? So if you have the, if I can get back to the right picture here, where'd it go? Just lost it. There it is. Okay, so that little triangle indicates that it is an edge trigger. All right, and so what it's detecting is it's detecting either the high to low or the low to high transition of the clock or the gate input. All right, and so this actually prevents noise from getting on the line, because if you're in this latch condition, well, I'm not going to go back to it, but if you're in that latch condition where the gate, as long as the gate is high, D passes through to Q. What happens if you get a little bit of noise on D? That's going to pass right through to Q and cause errors. All right. If you're just accepting D in on the edge, right? Whether you're going from high to low or whether clock pulse goes from low to high, you're only taking it at that one point in time. So you're much less susceptible to having a noise getting some noise on the line and causing an errant high that you don't want. Okay. So this is what essentially gets put inside of there if the chip has an internal edge detection circuit. Okay, so this is exploiting what we talked about in the first part of chapter 9, where we talked about the period of time that it takes for something to go from high to low or for something to go from low to high. What's the propagation delay? So if you have C feeding into this gate, right, it has an immediate effect on this input here. If it has to go through the inverter first, you're still either going to get a 0, 1 or a 1, 0, right? But for a brief, small little moment in time, because that signal has to be transformed through this inverter, while that's happening, during that propagation delay, you essentially have a high and a high on here, which is going to change the output. You get a little spike, right? So here we go. Here's CPD. That's this one, right? And you can see that just for, what is that, 20 nanoseconds probably, the CP changes from low to high, and it takes 20 nanoseconds to get through this NOT gate to change the input here, but that's just brief enough to get a high, all right? And when that happens, that's when it pulls D1 through and processes it through to Q, okay? So that's why we use the edge detection circuitry in there, and why we used edge trigger devices is because they are much, much less susceptible to noise and to error. Okay, so again, the synchronous inputs, because these are tied together, CP and the D input, the asynchronous, they don't care when the clock is going high or low or low to high. It just, whenever these get activated, they will change the output. Okay. And just more truth table for the same thing there. I think that's pretty much it for the discussion here on that. Any questions so far? I'm going to type it in the chat here. It's pretty straightforward. Like I said, everything I just talked about with the SR flip-flops and the D flip-flops should have been reviewed for you because we covered it in the in 112. And so hopefully I've spent a little bit more time in detail on some of these little things, because now we're going to take it even further when we talk about the JK flip-flops next time. All right, so if nobody has any other questions, that is all I have for tonight, and I will see you all next time we meet. Thanks very much.